Good morning, good afternoon, everybody, and welcome to the latest Canvas seminar. Today's speaker is Dr. Ryan Cloutier, who is a postdoc at the Center for Astrophysics at Harvard University. Ryan received his PhD at the University of Toronto under the supervision of Christian Minot and also of René Doyon from the University of Montreal. And today, Christian will be talking to us about testing radius valley emergence models around M dwarfs with Kepler, K2, and TESS.
Yes, so a couple of acronyms and a couple of interesting spacecraft that maybe not everyone here is familiar with, but we'll fix that by the end of the hour. So thank you, Dennis, very much. I'm excited to be here on this rainy Boston afternoon. So hopefully I don't cut out in the thunderstorm, but we'll see how that goes. All right, so good start. There we go. All right, so there's a few things I'm going to talk about. I'm going to begin with just sort of talking about the population of close-in planets and what we know about them, specifically from the Kepler and K2 missions, space missions. And then I'm going to highlight one particular system from the TESS mission, namely this TOI 1235b. And then if there's time at the end, I'd like to discuss some future plans that we have to do some planet population statistics with the extended mission of TESS, which actually just began like a week and a half ago. So I'm going to start off with the close-in planet population. So NASA's Kepler mission. So this is a space telescope that really revolutionized our understanding of planetary systems outside of our own solar system. And it did this by taking 4 years worth of data. So from 2009 to 2013, it stared at this one little patch of the sky that's about 11 degrees on each side, and it obtained precise photometry for these individual stars, for these individual sources, actually about 100,000 stars. And it was looking for transiting planets, right? A transit goes in front of that star, you'll see a dip, and you would see that in this 4 years worth of photometry from Kepler. And in those 4 years, Kepler actually found more than 2,000 planetary systems, something like 2,300 confirmed planetary systems. And most of these systems have architectures that look really different from our own solar system. So here, all these spinning dots are representations of Kepler planets. And you can see that they are more compact than our own solar system. So our solar system are these sort of concentric dashed lines, and then each of the individual solid lines are individual Kepler planets. And so, I mean, this finding in and of itself that there are all these compact planetary systems, it's an observational bias, but it does demonstrate that systems with multiple close-in planets are really common in the galaxy, right? And using these systems, we can try to turn back the clock and learn about the types of planet formation processes that can explain these types of compact Kepler systems. And then what kind of star and planet interactions might be going on in these close-in systems that we are not necessarily having ongoing in our own solar system. And so one of the most important results from Kepler, and in exoplanet demographics as a whole over the past decade or so, was the discovery of this bimodal feature, right? This is this bimodal feature in the occurrence rate of Kepler planets, specifically around FGK stars, which are basically sun-like stars. And so this is a very famous plot now from B.J. Fulton in 2017, and it's commonly known as the radius valley, right? And basically what you're seeing are the occurrence rates of planets, so the number of planets per star, as a function of the size of that planet. So because the Kepler team did this, this really awesome job of quantifying their sensitivity to detecting planets, you can correct for all the planets that you missed in your transit survey, and then you can derive the underlying planet occurrence rates, or like the real number of planets per star as a function of their size. And so in this paper, they combined those sensitivity corrections, and they got very precise measurements of the host stars themselves that allowed them to refine the sizes of the transiting planets. And consequently, they were able to resolve this bimodal radius valley feature for the first time. And so, what the heck are we actually seeing here? Well, clearly there's a dearth of planets, at around 1.8 Earth radii, right? That's the valley. And this turns out to be a consequence of the existence of a transition from small rocky planets that are like the Earth to larger non-rocky planets that host substantial gaseous envelopes that are up to like a few percent by mass. And so this is what we call the rocky to non-rocky transition. So right here, there seems to be a transition from small rocky planets to larger non-rocky planets. And one of the outstanding questions remains in that what process or what processes produce this transition from rocky Earth-like planets to larger non-rocky planets? And secondly, part of what I study is whether or not these processes are universal across the entire main sequence. So do the processes that sculpt the radius valley around the sun-like FGK stars, do those processes still dominate around the lower mass M dwarfs that I'm principally interested in and study during my PhD? So in the next few slides, I want to try and explain some, not all, but some of the proposed explanations for the emergence of the radius valley. And what are some of the testable predictions from those physical models? So the first one is a thermally driven atmospheric mass loss process that is driven by photoevaporation. So I'm going to try and illustrate that. So in the photoevaporation picture, you form planets early on. They have an Earth-like solid core with a mass M solid, and then they accrete a hydrogen and helium envelope. Excuse me. And then either because they formed in situ or they underwent some sort of disk-driven migration, they ultimately ended up on a close-in orbit at an orbital distance of A. And that distance A is typically much smaller than the Earth to Sun distance. It's typically, a few, maybe tens of % of an AU. So they're much closer than we are to our sun. And they arrive at these close-in distances within about 100 million years when the host star itself is still relatively active, and it produces this large flux of high-energy X-ray and UV photons with an basically this XUV luminosity that I'm calling L, XUV. And so at the planet's orbital distance of A, which again is typically much smaller than an AU is, the planet receives an XUV flux that is just given by the inverse square law, right? Luminosity over distance squared. And then this XUV flux then drives hydrodynamic escape of light elements in the planet's atmosphere, like the hydrogen and helium. So basically this XUV flux is stripping away either part of or nearly all of the planet's primordial atmosphere. So it's actually losing atmospheric mass. And now, if you do detailed hydrodynamic simulations that couple the XUV flux to the planet's atmosphere, as Lopez and Fortney did back in 2013, they derived the minimum solid planetary mass that is required to retain the planet's atmosphere as a function of the incident XUV flux. So you can think of it as planets that are less massive than this threshold value, given some X-ray flux. Those small planets will lose most of their atmospheres to photoevaporation, and they'll just be leftover solid cores. Whereas more massive planets that have sufficient gravity, they'll be able to hold on to those atmospheres. So this means that this threshold mass as a function of insolation flux marks the transition between rocky planets and non-rocky planets in this photoevaporation model. So if you then convert this, you convert the mass into a radius using a mass-radius relationship for solid Earth-like bodies, we see that the transition radius, the rocky to non-rocky transition radius, scales as the insolation flux to the 0.11, or similarly, for a fixed stellar mass, the transition radius will scale as orbital period to the 0.15. So why am I showing you these numbers? Normally, no one cares about the numbers, but what I want to communicate is that you can see that the transition radius itself is not a single scalar value, right? It's not as simple as saying that, all planets that are greater than like 1.8 Earth radii, they must have a significant gaseous envelope. They must be non-rocky. And that's because the transition radius itself, you can see, is dependent on the planet's orbital period. And secondly, the photoevaporation model itself predicts that the transition radius will actually get smaller with increasing orbital period, right? So like a 1.8 Earth radius planet, it might be rocky if it's on a very short orbital period, but the same size planet, but on a much longer orbit, might instead be on the other side of this transition, and therefore we would expect it to have retained much of its gaseous atmosphere. Okay, so this is a model prediction from photoevaporation, and we'll come back to it in a second. But before we do that, let's look at a second proposed mechanism for forming the radius valley, and that is gas pore formation. So here, instead of forming a population of non-rocky planets that then undergo some sort of atmospheric escape, like they did in the photoevaporation scenario, instead, here we're just going to form two distinct populations of rocky and non-rocky planets at early times out of the solid material in the disk, and after most of the gas has been removed from the inner regions of the disk. So that's why it's called gas pore. So you can basically just think of this as in situ planet formation during the transitional disk phase in a gas pore environment that happens during the first 10 million years or so. So in this setup, we're going to derive the maximum rocky planet mass by integrating the disk's solid surface density over the planet's feeding zone. So basically the zone around the planet where its gravitational influence is high enough that it can accrete solid, basically pebbles and form these protoplanets, which is proportional to this hill radius, this RH, which is given by this expression here. You can see it depends on A, which is the orbital distance of the planet itself. So if we now adopt a disk solid surface density from the minimum mass extrasolar nebula, MMEN, which is itself is proportional to the distance A to the minus 1.6. If we then integrate that solid surface density over the planet's feeding zone, we then end up with this maximum mass of a solid rocky planet and how it scales with orbital distance A to the 0.6, right? So we're going to do the same thing we did before. We're going to convert that mass into a maximum rocky planet radius. And that tells us that the transition radius now scales as orbital distance to the 0.16, or as insolation to the minus 0.08, or as orbital period to the 0.11. Okay? So, okay, fine. Again, we can see that this rocky to non-rocky transition, it's not a single value, right? It's dependent on the orbital period. But in the gas pore formation, in this new scenario, the dependence of the radius valley, or the rocky to non-rocky transition, its dependence on orbital period is positive now, such that the transition radius actually increases with increasing orbital period. And that's exactly the opposite behavior that was predicted by photoevaporation, right? So here I'm summarizing you the relations that we just derived, or the dependencies that we just derived. These are the theoretical predictions of the rocky to non-rocky transition on the insolation flux F and the orbital period P for these two models that could potentially explain the emergence of the radius valley. All right, these are just theoretical ideas. We want to be able to test them. So you can see that the predicted power law dependencies between photoevaporation and gas pore formation, they have the opposite signs, right? So photoevaporation has a positive flux dependence, whereas gas pore formation has a negative flux dependence. And it's just flipped for orbital period, right? And so this distinction, right, these different slopes, they provide us really with an opportunity to test these models against observations by measuring the planet occurrence rates, not just as a function of planet radius, like I showed in that bimodal distribution before, but as a function of planet radius and insolation, or planet radius and orbital period. And then in this way, we can measure the slope of the radius valley versus insolation or period, and we can compare that slope, the slope of that transition, to these model predictions to see if our data are consistent with either of these two models, right? So what do I mean by this? Well, here I'm just showing you one such effort. This is from Martinez et al. And they used the same sample of Kepler FGK stars that were used in the original BJ Fulton study. And what they did is they mapped out the occurrence rate of close-in planets as a function here of radius and insolation. And so you can see the two peaks. So I think everyone can see my cursor here. So you can see that there's this, the small rocky planet peak down here. And then there's the second peak of the larger non-rocky planets. And you can see that they recovered a radius valley slope that is positive. I know it looks negative here, but notice that insolation is actually increasing to the left. So this is a positive slope with insolation. And so now if you want to compare this slope to the model predictions, we can see that the measured slope is consistent with a thermally driven mass loss process like photoevaporation, but also that the slope really firmly rules out the gas pore formation mechanism, right? So this is one strong piece of evidence that suggests that the radius valley around these FGK stars in particular, around sun-like stars in particular, it can't just arise from in situ formation of super Earths in a gas poor environment, but you really need some additional process like photoevaporation to strip away planet atmospheres. And you need to be able to do that preferentially on small planets at high levels of insolation, right? So small planets will have low gravity. If you have high levels of insolation, they will preferentially lose those atmospheres around FGK stars. But in my final year of graduate school, back at U of T, I decided to look into whether or not this positive slope, does this continue to hold around the lower mass stars that were not included in this sample of stars? So namely, does this hold for the mid-Ks down to the mid-M dwarfs that I principally study? Now the problem with going about answering that question is that Kepler looked at an order of magnitude fewer mid-K to mid-M dwarfs than it looked at FGK stars. And the stellar parameters for many of those M dwarfs in the Kepler sample had highly uncertain masses and radii, which means that you had highly uncertain radii for the planets around those M dwarfs. And so these two problems would sort of compound and make it really difficult to resolve any kind of structure in the radius valley around low mass stars. And so to supplement the number of these low mass stars from Kepler, I decided to include results from the K2 mission, which is basically this second iteration of the Kepler mission that instead of just staring here at the Kepler field for 4 years, Kepler looked at, or K2 rather, sorry, looked at multiple fields along the ecliptic plane, but for shorter periods of time. So what happened? So basically, for those of you who don't know the story, back in 2013, the Kepler mission was ended because one of their reaction reels on board the spacecraft, it malfunctioned. And it prevented the spacecraft from maintaining its very precisely controlled pointing at the Kepler field. And really, so initially everyone thought, okay, well, that's it. Kepler's just done for. But after some really clever engineering, the mission was repurposed into K2, which uses the solar wind pressure to basically keep pointed along the ecliptic for basically 80-day intervals. Instead of 4 years, they only sit for about 80 days. But it requires, because the pointing itself is not that precise, it requires periodic thruster corrections to maintain some level of consistency in the pointing. But so it was still nowhere close to the pointing precision that we had from the primary Kepler mission. And what happens is, because you have this periodic drift and these periodic thruster corrections, it leaves the K2 photometry with these significant systematic effects that ultimately make the quality of the K2 photometry significantly poorer compared to the original Kepler mission. And that consequently makes K2 far less sensitive to finding transiting planets because the quality of the data is worse. But that degradation in sensitivity, right? How many fewer transiting planets are you going to detect in K2 compared to Kepler? It was never quantified by the Kepler team the way it was done for the original Kepler. But so despite that, I used a sample of 13,000 low mass stars from K2, for which I detected the detection sensitivity myself, basically by taking the light curves and injecting synthetic transiting planets into the light curves, and then running them through a custom-made detection pipeline. And what this allowed me to do was to derive a sensitivity correction similarly to what the Kepler team did for Kepler. And then I used updated stellar parameters based on the Gaia DR2 to basically derive this occurrence rate map, this thing that I'm showing you here. So the occurrence rate of close-in planets orbiting mid-K to mid-M dwarfs in Kepler and K2. So once again, I hope that you can convince yourself that we're seeing the radius valley feature again here in this radius insolation space. So there's this peak of the small rocky planets down here. And then as you move up, there's this sort of second peak, or maybe you see two peaks, but they basically have the same radius at about 2.2 Earth radii. So that's the bimodal peaks in the one-dimensional radius distribution. And so from this, it was able to go out and basically measure the slope of the transition between these two peaks, the rocky to non-rocky transition in this space. And that's basically what these gray lines are showing you. They're just different draws for different slope values, basically communicating what the uncertainty on the slope is. And just from looking at this, you can already see that it looks different from what we saw around the FGK stars, right? So if we compare them now slide by slide, if I compare the slope measured around the FGK stars, which is on the left, compare that to the slope that I measured around mid-K to mid-M dwarfs, which is on the right, you can see it right away, right? That the slope has flipped its sign, right? It's gone from positive to negative from the FGK stars to the mid-K to mid-Ms, right? It goes mass loss process like photoevaporation to then being consistent with the gas pore formation predictions around the cooler low mass stars on the right. So this was really the first detailed investigation of the radius valley around low mass stars. And we saw this flip in the slope and interpreted it as evidence that the dominant physical process that is sculpting the radius valley, it's clearly different in these two stellar mass regimes, right? So thermally driven mass loss seems to dominate around the FGK stars, but it becomes less efficient as you move towards the lower mass M dwarfs. So, what I would really like to do here is to construct these occurrence rate maps, but in very fine stellar mass bins, to see whether or not this shift in the slope is a continuous process as a function of stellar mass. And also, what is the stellar mass at which it goes from being positive to being negative? What is that transition mass? But, as you might imagine, we unfortunately do not have sufficient sample sizes of stars to do this kind of analysis in very fine stellar mass bins. But despite that, we still have these two competing hypotheses for where the location of the rocky to non-rocky transition is here in now planet radius versus orbital period space, right? So it's sort of analogous to radius versus insolation, but now I'm just plotting it as a function of orbital period. And so what you're seeing here are the same two slopes that I just showed you from the previous slide, right? So these two lines, the one on the left and the one on the right, one being predicted by thermally driven mass loss and the other by gas pore formation. And you can see that because they have different slopes, they naturally carve out these shaded subsets of this parameter space where the two models make opposing predictions regarding the bulk compositions of planets that sit in those regions. So you can think of this as, you can think of these two lines as two possibilities for the location of the rocky to non-rocky transition around M dwarfs. And so you can imagine that the models agree that any planets that are below both of the lines, so any planets that are down here in this region, those planets, because they're below the rocky to non-rocky transition, they should be rocky. They should be like the Earth. Whereas any planets that lie above both of the lines, they should be non-rocky. They should have a substantial gaseous envelope. But what if we consider a planet in say this large shaded wedge on the left here, this left wedge where my cursor is? According to thermally driven mass loss models like photoevaporation, any planets that sit in this region should be rocky because they are below the predicted location of the transition. But the gas pore formation model says that no. Those planets are actually above the transition, so they should be non-rocky. So this is a really powerful tool, right? Because we now have distinct predictions from these two models, and they give us the opportunity to test each of these models against each other by first identifying transiting planets that sit within either of these shaded regions. And then we should go after them and we should measure their bulk composition so that we can establish which of these two classes of physical model those planets' compositions are consistent with, right? And so again, around M dwarfs, because I like to focus on M dwarfs, there were only six transiting planets that had precise radial velocity or precise RV masses from the pre-TESS era. So I'll tell you about TESS in a moment, but there are these planets, there's these 6 planets that include, there's a couple from K2 here, and then there's this, 1214b and 1132b, and then the 2 LHS 1140 planets, which were both discovered by the, all 4 of them were discovered by the Ground-Based Mirth Transit Survey. And so they all got RV masses, precise RV masses, and I'm showing them here in this space with different shapes. So the different marker shapes, like whether or not it's a circle or a triangle, that's just indicative of the planet's bulk composition based on its RV masses and then its radii from the transits. So each of these 6 planets are either classified as being rocky. Basically, they're just like they're Earth-like bodies that are mostly iron and rock and with little to no atmosphere. Those are the circles. And then there are the larger non-rocky planets that require an extended gaseous envelope to explain their low bulk densities. And those are the triangles. And then there may be some planets with some intermediate composition whose masses and radii are really degenerate with the compositional models. So they're basically somewhere between being rocky and being gaseous, but we don't really know what they're made of yet. And those will be squares, but there aren't any squares in there yet. But so now, here is this space after we add all the new planets from the first 2 years of the TESS Transit Survey mission. And you can see that we've effectively doubled the number of planets within this space around the M dwarfs, right? We went from 6 to now I think there's 13 here. So TESS itself, TESS is an all-sky survey mission, and it's looking for really nearby transiting planets around bright stars. So stars that are systematically closer to us and systematically brighter than the Kepler stars were. But if you notice in this diagram, right, there still really aren't any planets with precise RV masses that sit within either of these shaded regions, right? And those are the planets that we're really interested in order to test these 2 competing radius valley emergence models. So, luckily, there are at least about 20 TESS objects of interest, or TOIs, around M dwarfs that actually do lie within this shaded region. And I say at least because I made this slide about a month ago and there's been data releases since then. So there might be a few more, but there's of order 20 planet candidates from the TESS mission that we want to target, or at least some of them, we want to target with RV instruments so that we can recover their bulk compositions and then test those results against the model predictions, right? So the TESS mission itself, it has a primary science goal. It has a primary science goal to measure the masses of 50 planets that are smaller than 4 Earth radii. And you can see on the y-axis, right? This doesn't even go up to 4 Earth radii. So all of these planets, all these TOIs would fit that science goal. And as part of my current job at the CFA, I'm trying to support the completion of this goal. First, by validating TESS super Earths and sub-Neptunes, particularly around M dwarfs, and then to measure their masses, right? To contribute to this goal of measuring 50 planet masses smaller than 4 Earth radii. And now in doing this, I'm actually trying to prioritize TESS planets that lie within either of these shaded regions so that they can contribute to completing the TESS science goal. And they will also provide valuable tests for the radius valley emergence models, the things that I'm pursuing scientifically right now. So along those lines, let's move on and let's talk about one such TOI that was only published, I think, like just a couple weeks ago it was published, and that's the confirmed planet TOI 1235b. So TOI 1235b is a super Earth, right? As you can see, it sits directly within the radius valley. It sits directly within this shaded region of interest. Here it is. And because it orbits a bright early M dwarf, we decided to go after it to obtain a precise mass characterization so that we can understand whether or not this planet is rocky or if it's non-rocky, which we can then compare to the 2 model predictions. But so before I talk about the results for 1235b specifically, I thought this might be useful opportunity to sort of give an overview for people who aren't familiar with how TESS objects of interest come about, and then how some of them, like 1235b, how some of those TOIs eventually become confirmed planets. So it all begins with the TESS mission. So TESS is the Transiting Exoplanet Survey Satellite, and it's equipped with 4 cameras that are basically stacked on top of each other. So that's these 4 squares. They're the fields of view of these 4 cameras. And altogether, these 4 cover about 4% of the sky, and they stay there. They stay pointed at this position on the sky for 27 days, right? And so these are the cameras. So this is basically one sector or one pointing that will last for 27 days. And after those 27 days, the spacecraft pivots basically on the ecliptic pole down here. It pivots into sector 2. And it stares at sector 2 for 27 days. And then it moves on to sector 3. And it just keeps going and going until it's covered 13 sectors over the course of 1 year. So 13 sectors, about 27 days each, gives you 1 year. And after that amount of time, you've covered the entire southern ecliptic sky, right? And then after that first year, TESS actually flips, and then it goes to the north. So now it covers in 13 sectors, so sectors 14 through 26. It covers the entirety of the northern ecliptic sky. So by the end of these 2 years, right, 1 year in the south, 1 year in the north, TESS covers about 85% of the entire sky for at least 27 days, right? There are these points, these pivot points at the north ecliptic pole and the south ecliptic pole that get, all 13 sectors at 27 days, but it gets 85% of the sky for at least 27 days. That's a dog. Now, the TESS primary mission, so the 2-year mission, actually, it only ended like a week and a half ago. It ended on the 4th of July. And so now for the past week and a half, we've actually been, we started the first sector of TESS's new extended mission. So TESS got a 2-year extension that's going to begin by basically repeating a lot of what it's already done. So it's actually began to re-observe the southern ecliptic sky. So it flipped back and it's redoing the south, basically to refine the parameters of the TOIs that it's already discovered. But it's also going to detect new TOIs, right? Ones that are typically a little bit smaller or have longer orbital periods than the TOIs that it discovered during its primary mission. And so after each 27-day sector is observed, the data are downlinked to the Science Processing Operations Center at NASA. And then an automated transiting planet search is conducted on all of the light curves, and it produces summary reports that basically look like this. So this is the summary report of TOI 1235 from sector 14. So there's a lot going on here, and the details aren't terribly important, but suffice to say that a validation team will then use this information, this data validation information, to vet the planet candidates, and then they ultimately will produce a list of planet candidates from each sector that will get released on a monthly basis. Okay? And then after those TOI planet candidates get released to the scientific community, we, the members of said community, will seek to validate those candidates as real planets in an effort that's coordinated by the TESS Follow-up Observing Program, or TFOP. And so TESS members like myself, and I'm sure some other folks that are listening in right now, will perform a series of observations. And these observations are designed to distinguish real transiting planets from false positives. So for example, TESS has really big pixels. And so you can imagine that with really big pixels, there could be many stars that it's monitoring that are blended with other nearby stars. And that means that TESS oftentimes cannot on its own uniquely identify which star a transit event that it is seeing is coming from. So subgroup 1, or SG1, which is one of the subgroups of TFOP, members of subgroup 1 will obtain seeing limited photometry from the ground to resolve the individual stars and try to confirm which star a transit event is actually happening on, or if that transit event is due to something that's not a planet. Maybe it's due to, you know, a background eclipsing binary that is happening on a fainter star that is close to the star that you think it's happening, and it makes it look like a transiting planet when really it's just a binary star. And so TFOP members will also get things like reconnaissance spectroscopy to try and look for stellar blends, or they might get high resolution imaging to spatially resolve stellar companions that are not resolved from the SG1 observations. And then the really what you want to do ultimately to confirm a planet is to measure its mass, and they do that as part of SG4, where they obtain precise radial velocity observations to measure the masses of those planets. And then there's also this last step, this SG5 step, to obtain space-based photometry that, you know, typically just gets ignored because of the limited space-based resources. So it's really these first four steps, SG1, 2, 3, and 4, that are the most common, and what we typically use to confirm test planet candidates, and basically what we did for 1235, as you'll see. So TOI 1235 itself, this is just a quick overview of the system so everyone's on the same page. It's a bright early M dwarf at a distance of about 40 parsecs. And if you remember the radius valley slopes that I was showing you earlier as a function of planet radius and insolation, remember that we think that the photoevaporation process is becoming less efficient as you move to lower mass stars, right? It went from dominating around sun-like stars to becoming less efficient around lower mass stars. And as you move to the M dwarfs, maybe the sculpting of the radius valley is becoming dominated by something else, by like gas pore formation process. Well, the temperature, the mass, and the radius of TOI 1235 place it sort of in that regime where we think this transition might be happening between photoevaporation and gas pore formation. So that makes this planetary system a real keystone system to help us to understand the origin of the radius valley around these types of low mass stars. So here, finally, is the TESS light curve, right? So this is the TESS light curve from sectors 14, 20, and 21, which all observed TOI 1235. And the target was observed at 2-minute cadence. So a brightness measurement every 2 minutes for a total of about 3 months. And this yielded 22 observed transits that are just phase folded down here in the bottom, where you can clearly see the transit at a fairly high signal to noise when you stack all the transits on top of each other. This is a signal to noise of about 20, so relatively high. And so here's just an example of one of the TESS images from that sequence, where the white outline is the photometric aperture. And you can see that each individual TESS pixel, they're big, right? They're quite large. And there's actually about 15 of these circles. There are about 15 nearby Gaia sources that could be contributing to contaminating this light curve. So what you want to do is get that seeing limited photometry, right? You have an approximate period and a transit time from the TESS light curve. So we went out and we observed a transit at the time we thought it was going to show up from the ground to, firstly, we're going to confirm that the transit arrives on time, right? So that we got the period right. And secondly, to confirm that the transit is actually occurring on the star that we think it is, right? Is it actually coming from TOI 1235, or is it from some other source, one of these other nearby sources? So the reason we do this, again, with the ground-based observations is because those pixels are much smaller, right? So here in the image on the right, you can see the source, right? You can see the individual source, and that's because the individual pixels here are about 0.4 arc seconds per pixel, compared to TESS's really big 21 arc second pixels. So you actually observe the star, right? It's this bright source here in the middle that was taken from the ground with the Las Cumbres Observatory's Global Telescope Network, one of the McDonald telescopes, the 1 meter McDonald telescope. And here is that ground-based light curve in this bottom panel here. So this is just one transit that we got from the ground compared to the 22 transits that we got from TESS. But so because we had this observation from the ground, we confirmed that the transit was in fact coming from TOI 1235 as we expected, and that the transit basically arrived at the expected time. So we got the period right. And those are these values P and T0. And so taking all these observations together, we were able to derive the planet's ephemeris itself and its radius, so about 1.74 Earth radii. And then together with some other follow-up observations that I'm not showing you here, but things like reconnaissance spectroscopy and adaptive optics imaging, we're able to rule out false positives. So we validated TOI 1235b as a true planet. And so that fact now gives us the confidence to invest the time with our RV instruments to pursue a planetary mass measurement, which in my case uses the Harps North spectrograph in the Canary Islands. And so here is on the left, our raw RV time series. So we've got 27 RVs here from Harps North, plus we got 11 RVs from high-res that were shared with us from by the Keck team, basically in California and in Hawaii. They shared 11 RVs. And then to the right is the generalized Lomscargo periodogram, which is basically just a frequency spectrum of the RV time series. And you can see that it's dominated by this strong peak, this strong periodic signal at 3.44 days, which is exactly the planet's orbital period, right? So that's the planet signal showing up in our data. And then we proceeded to model these RVs with a planetary orbit, plus a treatment of residual correlated signals from stellar activity using a Gaussian process regression model. So on the top, I'm showing you the raw RVs and the periodogram after we remove the GP activity model. So you should just be seeing the planet plus some noise. And then in the second row is just the RV residuals. So once we subtract the planet off. And you can see from the periodogram that there are no more strong signals, right? All of these peaks seem to be sort of buried in the noise. So our model seems to be complete. It doesn't seem that we're missing any additional signals. So, I mean, you can imagine that if there were a second planet in the system, we might be able to see a peak in these residuals because we didn't explicitly include it in our model. But because we don't see any peaks like that, we think that our RV model is complete. And so with that, you can phase fold the RVs to the planet's orbital period, which shows this clear orbital signature from the planet with an amplitude of about 4.1 meters per second, which corresponds to a planetary mass of about 6.9 Earth masses, or a bulk density of 7.4 grams per cubic centimeter, which is about 33% denser than the Earth. And so now that we have the planet's mass and its radius, we can add TOI 1235b to the mass radius diagram of M-dwarf planets that have precisely measured masses. And so you can see that 1235b, it's this triangle here, it sits very close to this Earth-like compositional curve. So a planet with a 33% iron core mass fraction, plus a 67% rocky silicate mantle, and basically no atmosphere. And so you can see that 1235b also sits basically right on top of this second planet, this second marker right behind it, and that's 1140, LHS 1140b. And so these two planets, 1235b and 1140b, they seem to represent nature's limit on the maximum mass of a terrestrial planet, in that there are no planets with Earth, like along this Earth-like compositional curve, with masses greater than, I don't know, 8 or 10 Earth masses, right? You likely cannot form a rocky planet that is more massive than 8 or 10 Earth masses without that planet accreting a significant size fraction in its gaseous envelope. So now that we know that TOI 1235b is a rocky planet, it's basically just a scaled up version of the Earth, we can now go back to this diagram, our favorite diagram of the radius valley versus orbital period and planet radius, and we can add 1235b as a circular marker, right? It's a circular marker because we've determined that it's rocky. And so right now we get to do the fun part, right? We get to compare this new result to the two model predicted slopes of the radius valley. So because the radius valley line, remember that it marks two possible locations of the rocky to non-rocky transition. So any planets that are below the radius valley line are expected to be rocky. So now that we know that the composition of 1235b is rocky, that means that it's only consistent with this dashed line. It's only consistent with the thermally driven mass loss model, right? And because it's above this solid line, the gas pore formation model, it is inconsistent with the gas pore formation model, because the gas pore formation model says that TOI 1235b should have been non-rocky, but it's not. It's a big rock. It's a big scaled up version of the Earth, right? So based on this analysis, we concluded that thermally driven atmospheric mass loss from a process like photoevaporation, that process has to have remained efficient at sculpting the radius valley around early M dwarfs, right? This planet orbits an early M dwarf. And so, and furthermore, if my original hypothesis was true, that gas pore formation starts to become the dominant physical process as you move to lower and lower mass stars, then that transition from photoevaporation to gas pore formation, that transition has to occur around stars that are less massive than TOI 1235, which is, to remind you, about 0.64 solar masses. So because this new rocky planet shows us that thermally driven atmospheric mass loss is still efficient at that stellar mass. So if indeed gas pore formation does become the dominant process at some point, it has to happen at a lower stellar mass than 0.64 solar masses. But of course, I mean, this is only one planet, and I'm trying to generalize to the full M-dwarf planet population. So really, more M-dwarf planets within these shaded regions, within the radius valley, are going to have to be characterized precisely with radial velocities, and that is a continuous, ongoing effort that I'm still involved in, and many other teams are continuously involved in. Excuse me. So that was a lot to take in. And I think in the interest of time, I'm going to sort of skip over our future directions. So things that we were thinking about using the TESS extended mission for. We can talk about it in the questions if you really like, but I'm just going to skip over it for now. And I will end with my summary, which begins with, again, there are multiple physical mechanisms that have been proposed to explain the emergence of the radius valley. There are these thermally driven mass loss processes like photoevaporation, but then there's also this gas pore formation scenario. And the dominant physical mechanism appears to be stellar mass dependent, right? The radius valley slope around the FGK stars favored thermally driven atmospheric mass loss, whereas the radius valley slope begins to favor gas pore formation around early to mid M dwarfs. And then lastly, the super Earth TOI 1235b, it suggests that thermally driven mass loss is still efficient around early M dwarfs because it has an Earth-like composition that is consistent with thermally driven mass loss and not with gas pore formation. And then there's the last point with regards to the extended mission. So I will end there, and thank you very much.
Hey, better than nothing.
Thank you.
Okay. Hold on a second here. I need to exit full screen. Okay, the preferred way of asking questions is to raise your hand using the appropriate button in the participants list. But we do have a few questions that have already come in by the chat window. So Eve, do you want to ask your question verbally, or would you prefer I read it out?
I can see it. So going back to the two lines that you drew in the radius versus period diagram, I was wondering how you drew the normalizations because they do depend on unknown parameters. So for example, the photoevaporation does depend on the unknown magnetic field intensity of the planet. And for the, well, you call gas pore formation, but anyways, that one, how you draw, it's subject to the assumed disk solid surface density. So I was just wondering whether you could talk about how you drew those normalizations.
Yeah, no problem. Thanks, Lee, for bringing it. Thanks, Eve, for bringing it up. I was hoping you would be here to sort of fix everything that I was saying wrong about gas pore formation. Basically, what's happening here is the slopes themselves are coming from the model predictions, the things that I sort of derived in a hand wavy way early on. but the normalization is coming from the observations themselves. So these locations of the radius valley are basically giving us the normalization. So it's the slope comes from the theory, the normalization comes from explicitly these slopes. So this line for the thermally driven mass loss, and then basically the average of these gray lines here for the gas pore formation scenario.
Okay, thanks.
And Ping, would you like to ask Ryan your question?
Sure. Just was interested in how you're going to be planning to select additional candidates to test the models further.
Are you talking about these TOIs that sit in this region?
Yes, right. Yeah.
Yeah, I mean, so there's a whole bunch of considerations that go into choosing potential RV targets, and the RV teams themselves are big scientific collaborations. So it's not solely up to me, right? I have to sort of make my pitch and say, hey, you know, this TOI here, for example, is interesting. Let's go after that. So I will make a pitch, and it's usually based on the amount of time that we think is required to get a significant mass detection out. So stars that are very faint are no good. Stars that are very active are typically sort of frowned upon. You know, fast rotators, things that will take a large investment in RVs will basically be ignored. And then, of course, TFOP is this huge collaboration of international teams. So there are many RV teams that will be looking at the same TOIs. So oftentimes, what will happen is if, you know, say there's another team in California or Europe or somewhere or Australia that are looking at a TOI that we're interested in. If they've already begun and have, you know, a significant number of observations, then we're not going to try and step on their toes. We'll let them have it and invest our time elsewhere. So there's all these factors that come into play.
Yeah. Thanks for the insight. It's interesting to know that process.
Thanks.
Joanna, would you like to ask your question?
Sure. Hi, Ryan. Great talk. I just wanted to know, I know we don't have that much time, but could you say a few words about that last part of your talk that you had to skip over, and extended mission plans?
Extended mission plans, yeah. So basically, and so I've talked about using RVs to distinguish between thermally driven mass loss and gas pore formation, but there's these model predictions. So there's gas pore formation, there's photoevaporation, and then there's this third model which I haven't talked about. And basically, you can see that they make different predictions for how the radius valley depends on stellar mass. And you can see that here in the sort of in sun-like stars, and then TOI 1235, it sits sort of around here. You can see in this region, basically to the right of my cursor, the models are not very discrepant. And there have already been sort of measurements of how the radius valley moves as a function of stellar mass. And what I'm saying is basically you want to go down to the really low mass stars where the models actually become discrepant, right? They're not all sort of clumped together. You can actually tell the difference. But because not very many of those stars have been observed, the error bars just shoot up and you can't do anything interesting. So we proposed to, in the TESS extended mission, to specifically target these low mass stars, these mid M dwarfs. And in that proposal, we said that if we can get about 12,000 of them, and specifically selected ones, a specific set of 12,000 mid M dwarfs in the TESS extended mission, so in 2 years of TESS, 2 more years of TESS, that will be able to derive this sort of error bar. And that sort of error bar will allow you to distinguish between, say, photoevaporation and gas pore formation at something like 3.5 sigma, which would be fantastic. So that was a proposal that went in, and now that the TESS extended mission has started, we're going to start looking into those data as they come in. It's great.
I sort of have a related question, maybe. Do these photoevaporation models take into account any evolution of the far UV flux from the M dwarf?
So it depends on which explicit model. Like there are different versions of this, right? And as he alluded to, some of them include things like magnetic fields and whatnot. But a lot of them will extrapolate to what a star's early XUV history was like, because I mean, like we don't know what the XUV environment of, say, 1235b looked like in the first 100 million years or so. And that's really when photoevaporation is at play. Photoevaporation only dominates for the first 100 million years or so. And so when you look at stars that are many billions of years old, you sort of just have to extrapolate based on, UV spectra of similarly spectral type stars that are young. But it's not known explicitly for the individual sources, unfortunately.
Right. So how solid, or would you say that photoevaporation curve is?
This particular curve?
I mean,
this is a theoretical prediction that I don't recall the details of it, but it's, I mean, I wouldn't believe it to like the level that it's plotted here, right? There's always going to be some wiggle room, and I don't remember exactly what it is, but it is true that based on the theoretical predictions, you should see a fairly discrepant prediction between, say, the dashed curve and the dotted curve in the low mass regime.
Okay, thank you. Any more questions for Ryan? Jean Malone, go ahead and ask your question if you wish, or do you want me to read it out?
Okay, I can ask it. If you can hear me, can you?
I can.
Okay. I didn't catch where you obtained the RV observations for TOI 1235b. I guess you must have gotten, you had a small k and you had the mass and density.
So the RVs themselves, there were 27 that we got from Harbs North, which is an optical. An optical. Yeah, sorry.
Okay, well, if there are no further questions for Ryan, I'd like to thank you for a very interesting and engaging talk. Thank you for taking the time to share your work with us. Thank you, everybody, for participating, and look forward to seeing maybe some of you at next week's talk. So have a good week, everyone.
Thank you.